Welcome to the deep dive. So today we are jumping into some of the really dense critical components that keep the modern industrial world running.
The unsung heroes, really.
Exactly. Forget the flashy interfaces, the control screens. We are talking about the real mechanical grunt work.
We are diving into control valves.
Yeah.
I mean, they're often called the final control elements of any fluid system.
Right.
If you're talking about a refinery, a chemical plant, a water treatment facility, these valves are the only things physically manipulating, energy managing flow, pressure, all of it.
And their job is basically to keep things safe and reliable.
That's the whole
And
point.
for this deep dive, we're getting specific. We're focused on the true workhorses.
Oh.
Reciprocating control valves.
Or what most people would call sliding stem control valves.
Right. So we took these incredibly heavy, dense technical training manuals for instrument techs, the same they use on the plant floor.
Yeah, not light reading.
Not at all. And our mission here is to basically pull out the core engineering dilemmas, the high-stakes maintenance knowledge, and just give you a serious shortcut to understanding it all.
It's a foundational layer of knowledge. At their heart, these are just mechanical devices. They regulate flow from a high-pressure area to a lower-pressure one.
And every single one is made up of two major parts.
Two integrated components? Yep. You've got the actuator, which is the power, and the valve body, which has all the guts that actually regulate the flow.
Okay, let's unpack that. We should probably start at the top with the actuator, the power source. What's actually making it move?
Well, in the vast majority of industrial settings, the answer is just air.
Air.
Yep. The source material really focuses on pneumatically operated diaphragm actuators. They take clean, dry instrument air from the plant and use it to create thrust.
So it's like a constant mechanical tug of war then, right?
That's a perfect way to put it. The air pressure pushes on this flexible diaphragm, creating a downward force.
But something has to push back.
Exactly. And that's a big, calibrated mechanical spring. The actual force, the thrust that moves the valve stem, is just the result of that ongoing fight.
Yep.
Air pressure versus spring force.
And that thrust travels down to the valve body, which is what's actually interacting with the fluid.
Correct.
So if we break down the valve body, the first piece we hit is something called the bonnet. What's its main job?
Its primary critical job is sealing, just keeping the process fluid contained.
Okay.
And you can think of it in two parts. First, there's the bonnet gasket. That's a static seal between the main valve body and the bonnet itself.
Like a seal on a jar lid.
Exactly like that. And then you've got the part that handles the movement.
The dynamic part.
That's the stuffing box.
Mm-hmm.
This is the seal that wraps around the valve plug stem, and it's absolutely essential because that stem is constantly sliding up and down.
Reciprocating.
Right. And the stuffing box stops the process fluid from leaking out along that moving stem.
And then finally we get to the core of the operation, the parts inside the valve that are actually touching the fluid.
Yes, and these parts are known collectively as the trim.
The trim, okay.
The trim is really the heart and soul of the valve. It's four critical pieces. You have the valve plug stem, which connects up to the actuator.
Right.
Attached to that is the movable valve plug. That's the physical piece that restricts the flow.
Okay. And that plug sits in a seat.
It does. The seat is the ring the plug contacts to create the seal for closure.
And what about the cage? That sounds important.
The cage does two jobs at once. First, it guides the plug's precise up and down movement. But, and this is the really interesting part, the windows cut into the side of the cage. Their geometry actually determines the flow characteristic. You know, how the flow changes as the plug moves. Does it open fast, linearly? That's all decided by the cage.
So the trim is basically the replaceable heart of the valve, and it dictates the flow characteristics.
You've got it. That's a perfect summary.
Okay, let's talk about the high-stakes engineering side of this. If you lose instrument air, which, happens, you cannot afford to have the valve do the wrong thing. So now we get into fail-safe design.
This is where control designers really earn their pay. They have to select a valve's default position, either fail open, FO, or fail closed, FC, to prevent a major hazard.
Like overfilling a tank.
Exactly. Or a pump running dry. This choice dictates the actual mechanical components they have to pick.
And this is where it can get a little confusing for people because you have two separate actions to think about. The actuator's action and the valve's action.
Right. Let's start with the actuator, the power input. It can be direct acting or reverse acting.
Okay.
A direct acting actuator means that when you increase the air pressure, the stem extends or pushes down.
More air, stem goes down.
Simple as that. The air is usually connected on top of the diaphragm.
And reverse acting is just the opposite.
The opposite. You increase the air pressure and the stem retracts or pulls up. In that case, the air is connected below the diaphragm.
Got it. Direct is push down, reverse is pull up. Now we have to look at the valve body itself. It also has a direct or reverse action.
Yes, a direct acting valve is set up so that pushing the stem down causes the valve to close.
And a reverse acting valve.
Pushing the stem down causes the valve to open.
And this distinction is everything because the fail-safe position is all about how you combine these two.
It is. This is a huge takeaway. There are 4 possible combinations.
Let's run through them. So if you have a direct-acting actuator,
Pushes down on power,
and you pair it with a direct-acting valve,
closes when pushed down.
then the result is air to close.
Right. When the air fails, the spring takes over, pulls the stem up, and the valve opens. So it's a fail-open setup.
But if you use that same direct-acting actuator and pair it with a reverse-acting valve,
The whole thing flips, and now it's air to open.
because when the air fails, the spring pulls the stem up.
But pulling the stem up closes a reverse valve. So you get a fail-close system. The loss of air shuts off the flow.
And you can get that same fail-close result with a different combination too.
You can. A reverse actuator plus a direct valve also gives you fail-closed. It's all about selecting the right mechanical combination to force the safest outcome when power is lost.
It's mechanical redundancy just built right into the design.
Precisely.
Okay, now let's move into the actual hardware, starting with the real workhorse of flow control, the globe valve.
Right. Historically, it had a spherical body, which is where the name comes from. It's known for having high pressure losses because the fluid has to make these 2 sharp turns inside.
And this is where the design trade-offs really start to become clear.
This is the central design dilemma, really. You have 2 main types.
Single-ported and double-ported.
The single-ported globe valve is the undisputed champion of isolation. It can get you what's called tight shutoff. We're talking less than 0.01% of maximum flow leakage.
That sounds incredible. Why wouldn't you just use that everywhere?
Because of physics.
Yeah.
I mean, if you have a high pressure difference across that valve, that fluid pressure puts a massive lifting force on the bottom of that single plug.
So to close it, you have to fight against all that pressure.
You do, which means you need a huge, powerful, and, very expensive actuator to force it shut.
Makes sense. So what's the solution when you need high capacity, but you don't want a monster actuator?
You go to the double-porting globe valve. It's often called the semi-balanced design. It uses 2 plugs on one stem.
How does that help?
Well, the pressure pushing up on the bottom plug is mostly canceled out by the pressure pushing down on the top plug. The forces are balanced.
That seems like a huge benefit. So what's the trade-off? What's the hidden cost?
The compromise is simple. You cannot guarantee tight shutoff.
Ah,
Because of tiny manufacturing differences and how materials expand with heat, the leakage can be way higher, up to 0.5% of max flow. If you need absolute isolation for safety, that's just not acceptable.
so you're trading that tight closure for a smaller, cheaper actuator.
That's the engineering calculus, plain and simple.
Let's touch on a few other specialized globe types from the sources.
Sure. The angle valve is a clever one. It's basically a globe valve with a 90-degree exit, so it acts like an elbow in the piping.
And why would you do that?
It's great for highly erosive service. The fluid path is more streamlined, which really cuts down on wear and tear.
And then there's the 3-way valve. That's for mixing fluids, right?
We're diverting them.
Yeah.
They're essential in things like heat exchange systems. You can use one as a mixing valve with 2 inlets combining into 1 outlet, or as a diverting valve where 1 inlet splits into 2 outlets.
It routes the fluid without needing 2 separate valves.
Exactly.
This brings us to a more modern update on the globe valve, the cage-guided valve. They seem like they were designed specifically to make maintenance easier.
They absolutely were. That's a key advantage. The entire trim, the plug, seat, and cage could be pulled out as 1 unit just by taking off the bonnet. No wrestling with internal threads.
And the cage style also led to the fully balanced plug cage style valve.
Yes, this is a really sophisticated solution to that actuator size problem. It uses a small balancing port to equalize the pressure on both sides of the plug.
Which again means you can use a smaller actuator.
It does. But again, you are still trading away tightness. It uses a sliding piston ring seal, and tight shutoff is just not possible.
That leakage trade-off really is the universal constant here. It's fascinating.
Shifting gears a bit, the sources also covered some really specialized services, like handling fixed slurries or corrosive mining waste.
For those, you see diaphragm valves and pinch valve.
Right, the diaphragm valve, or Saunders valve, uses a reinforced diaphragm to seal the flow. It's great for dirty or viscous stuff and often gets rid of the stuffing box entirely, but they're usually limited in size.
And pinch valves are for the bigger slurry jobs.
Yeah, from 1 inch up to 24 inches. They literally just squeeze a flexible internal tube shut.
Okay, so we have the valve, but how is it actually held into the pipe? The sources contrast three common connection types.
The simplest are just screwed pipe threads, or NPT. They're cheap, but they're really only for smaller sizes, maybe 2 inches, and they are a real pain to remove for maintenance.
Then you have what you see most often in industry.
The bolted gasketed flange. They're easy to remove, and they can handle huge pressures and temperatures up to 815 degrees Celsius.
And for the really extreme conditions.
For extreme high pressure, you'll see a specialized ring-type joint flange, or RTF.
And the last one is the most permanent option.
Welded ends. They're totally leak-tight and cheaper to construct, but obviously they're very expensive and difficult to remove.
And there's a huge safety point there for maintenance.
Oh, absolutely. If you're welding a valve in line, you have to remove any trim parts made of, say, composite materials first. Otherwise, the heat will just destroy them.
So let's talk about extreme environments. If the fluid is incredibly hot or cold like cryogenic, down to minus 270 Celsius, you have to protect that packing material.
You do, and that's where the extended bonnet comes in.
Yeah.
That extension just provides a buffer zone. It keeps the heat or the cold away from the packing.
So in cryogenic service, it stops the stem from frosting over.
Right, which would just shred the packing seal every time the stem moved.
And for those absolute highest stakes situations where any stem leakage is completely forbidden.
There's the bellows seal. It uses a welded stainless steel bellows to totally contain the process fluid. It's an incredibly high-integrity seal.
And they even have a backup warning system built in.
They do. They're pretty cool. They include a pressure tap outside the bellows. If that main seal ever fails, the tap immediately detects the leak, giving you a warning before anything escapes.
Now that we understand how they're built, we have to talk about working on them. And the training material really emphasizes safety. These things, even the small ones, come with universal, severe hazards.
The source material lists 7 that technicians have to respect. You have high-pressure process fluids, up to 24 megapascals, which is brutal.
Then there are chemical and corrosive risks.
Yeah, that means intense decontamination acid bathing, steam cleaning, before you can even start a teardown. Plus, you have electrical power, extreme temperatures, all the usual industrial risks.
But 2 of the hazards are really intrinsic to the valve's design. The first one is pretty obvious: pinch points.
Moving parts. They can cause serious injury if the valve cycles while you're working on it.
But maybe the most insidious hazard mentioned is the stored spring energy.
This is a major, major danger. The springs in these actuators can exert phenomenal force. We're talking tons of force, even when all the instrument air is gone and the plant is shut down.
Wait, hold on. So even if the plant is down and the valve is just sitting there, that spring is still fully loaded and dangerous.
Exactly. The source is very clear that technicians have to follow the manufacturer's procedures to the letter to make sure all that stored energy is safely released before they even think about separating the actuator from the valve.
Because that stored compression could be lethal if it's released unexpectedly.
Absolutely lethal.
That mechanical danger is one reason that maintenance is changing so dramatically. We're moving away from reactive work and into the era of smart diagnostics.
Yeah, often done while the valve is still operating or in line. This is all driven by advanced microprocessor-based valve positioners, like the Fisher DVC 6010 mentioned in the source.
They're like tiny health monitors attached to the valve.
That's what they are. They collect data and let you verify performance without ever having to pull the valve out of the line, which prevents the kind of failures that lead to really costly downtime.
So tell us about some of these diagnostics. What can they actually do?
Well, the air mass flow diagnostic is a perfect example. The positioner constantly measures the steady-state air consumption of the whole assembly.
Okay.
For some of these controllers, normal consumption should be less than, say, 14 standard cubic feet per hour. That's a tiny amount of air.
Very small.
Precisely. If the diagnostic report suddenly flags consumption over 30 seconds off, the system knows immediately that there's a problem. A micro leak, a damaged diaphragm, a failing relay.
It catches leaks you could never hear or see.
Long before they cause any real process instability. It's incredible.
So it's using a digital sensor to find a microscopic mechanical flaw. What other health checks do they run?
They do a supply pressure diagnostic to check for problems, and they look for something called droop, a pressure drop in the air supply when the valve has to move a long way,
And that would indicate a restriction in the airline.
or a problem with the regulator. It affects the valve's ability to respond quickly. They also monitor friction and dead band, trending to detect wear and tear before your process control quality starts to degrade.
But sometimes the damage is just too great, and the valve has to come out for a full overhaul.
Right. The hands-on work. It starts with decontamination, of course.
And then disassembly and the really specialized work begins.
That's when you get to the process of grinding, or lapping the plug and seat. Technicians use these fine compounds to polish the metal surfaces until they get perfectly uniform, smooth contact for that tight shutoff.
And I noticed a final point on the stem itself. The guidance says a marred stem almost always has to be replaced with a factory part.
Yeah, that's because the packing seal's whole life depends on extremely fine, polished finish on that stem. If it's scratched or marred, it just won't seal correctly, and trying to replicate that factory finish in the field is basically impossible.
It really highlights the fine tolerances involved in these massive, heavy-duty components.
It does.
So what does this all mean? We started with the control valve as, a simple mechanical switch on or off, and we've really revealed it to be this complex matrix of engineered trade-offs.
The key takeaway, the synthesis, is really that calculus of compromise. If you need absolute isolation, that 0.01% leakage for safety, you have to accept the cost of a giant actuator for a single ported design.
But if you need a smaller, cheaper actuator,
Then you have to accept unavoidable leakage by choosing a balanced cage or double ported design. Every single choice, from the seal to the flange, is a deliberate calculation of risk versus reliability.
which brings us to our final provocative thought for you to think about.
The control valve is a machine that is designed to withstand just physical brutality pressures, up to 40,000 kPa, temperatures near absolute zero. Yet, the sources make it very clear that the future reliability of this heavy mechanical system,
Uh-huh.
it now rests entirely on the integrity of a handful of digital data streams. Industrial safety is no longer just about the strength of the metal, it's about the precision of the diagnostic data flagging an air leak of over 36A.
So how quickly will that digital health monitoring completely reshape our understanding of uptime and safety in these high-stakes environments?
The shift from pure mechanics to data analytics is already defining industrial reality.